Start streaming. Hey Ted, what are you doing on your computer that's more interesting in chemistry? What?
The notes.
No, put it away. Concentrate on these notes.
The other section of the notes.
Pardon?
I don't the other section of the notes.
You don't have the newest section?
Yeah.
So why, they're just at the back.
They're at the back.
Yeah, I always have extras. The front page looks like this. PLOE, dynamic equilibrium. Got it? Okay. Literally just took a selfie.
All right.
Okay, we got everything for that? No, we don't. No, you're going to Hawaii, but you still have to work.
I'm ready to work. I'm ready for you to do
No, notes out. We're doing them right now. You're doing that one. Put that away. Get on your notes. Write things down. What do you think they're going to do? You're increasing A. Think about what's going to happen with the rate. This is concentration. Think which way it will shift. Okay? Okay? So this is the reaction.
The reaction shifts
I will admit that pen right there is kind of intimidating. I feel like you can just like grab my head and slam and then I'd be dead. Intrusive thoughts. So you're going to increase the concentration of A all at once. How will that change what's going on here? What will you get more of and what will you get less of? Does that make sense? You've got something? Good. You got something? Okay.
Not a rest, but
Yeah.
Nice.
Oh, yeah. I haven't done that. I will. You've got.
you don't have plateau.
Okay.
Bullshit from your
Something A. I don't know.
Right now, what do you think we'll have? Put away your laptop. This is discouraging.
Show me a little, right?
No, put away laptop. Put away. Put it away.
If it's off, it's like,
No, because you just turn it back on again. And
That's
then you,
cool.
And then you play a bumper
That's
cam.
like cool.
Okay. Put it away.
For like this part of this part.
Is it just because
Oh, here.
your background's
So like
moving?
here, we wrote.
Microsoft has that link.
So as it's like.
It
As
was
long as
a-
like 14 of those.
No, but they eventually stop because that'll
And then
drain
it's
your
supposed
battery
to
so fast.
decrease
Yeah, that's up to
and
you.
go back to like
Yeah.
equilibrium. They're
Laptop
all,
away?
like eventually like the same.
No, but you're writing things down and actually drawing
And
them.
so
I know.
go to B.
So put that away.
There's an issue.
What's the issue?
Decrease.
Because I don't have the things.
But as I just told someone else,
And
then you come get it.
Will also increase.
Right?
You're gonna start out.
But you can have extras in case you lose it.
And then level out.
So put away laptop.
I need
So basically you
Two,
just follow
four?
like these three things.
What do you need?
That makes any sense. I don't know.
Someone's got eyes.
What did you
Oh, I
write?
can move you
Oh my
up.
God.
No, it's okay, but he needs to sit back here.
Put away laptop.
What is going on with you today?
Put it in your bag. Off, because they don't want to have to constantly monitor it.
Again.
You all saw that.
How are we supposed to open?
I know. You may be, okay. This was decreasing the concentration. If I decrease the concentration, which way? Forward and reverse. We've got, let's do blue is forward, green is reverse. If we decrease the concentration, what happens to both rates? They're both going down. Which one does that affect the most? The reverse. You can't do very much if you have even less. This is plus heat, so this is this type of graph. It needs energy more, just like it was the most affected before. And it can do it. Now it's the most affected again. So which way is it going to shift? To products. And that means for a rate graph, they both decrease. We'll put that as T1. They both decrease, but which one decreases the most?
The blue.
Hands up if you think forward. Hands up if you think reverse. I tried to make my face look the most puzzled on that one to try and fool you, but some of you were not fooled. Like my analogy yesterday, if you have two people who need money and you give the one who has less money more money, it affects them more. The person who's living paycheck to paycheck does the most. Also, same thing, if you take away something, you're living paycheck to paycheck and you get a fine for speeding, it's going to affect you way more. For a millionaire who's speeding, that's just a fee to be allowed to speed, like it doesn't matter. And so for this side, taking away the energy didn't matter as much, it doesn't need as much. Whereas this side matters a whole lot. And so the reverse rate, the side with the heat term, that's going to be affected the most. So it's going to decrease the most. It's going to go down. Blue is also going to go down. Then what's going to happen for a rate? Even, just straight like this.
It's gonna like.
Yeah, they're going to kiss. So they're going to come up and then even out because this one, reverse rate, now it's going to get, the other one's going faster, so it's going to throw more things to that side. If it's throwing more things to that side, then that rate will start to increase because the concentration is increasing, and this one will start to decrease until they both match. And then they kiss. And equilibrium is established. In terms of concentration, which concentration is going to go up? AB. It's not able to throw things. It's going to accumulate on this side. That rate got slower, so AB was going along. And then it started to increase. Rapidly right away, and then comes off, and then you get a straight line. What do A and B do? Decrease. In what ratio? No? I changed the example. If you didn't change your example, there's 2 B's for every 1 A.
1 to 1.
So, pardon? It's not 1 to 1. Because 2 B's react for every A. I changed the example. Just to emphasize that. So it should be 2 to 1. So B will go down twice as much compared to A. If this is A, then what? That should be B. Now I've confusingly labeled it because they're overlapping, but B, A, B, A. So that this, if that distance there is X, then that distance there should be 2X. They should be in a 2 to 1 ratio because 2 B's get used up for every A. So check your work from last day. Everybody said they had it. Andrew? You were staring at it like you had a question, so I just said you.
I was gonna ask if I need a water bottle.
If you need a water bottle, what? Where is your water bottle?
It's not good. But it's in Whittles, it's like 2 minutes.
We're going to do another. How about if you answer the next question? If concentration of A increases, what will the concentration of B do?
It shifts to the flanks.
Concentration of E.
Oh, I didn't, B will.
I think maybe you should stay here for this slide.
Yeah.
Okay. But when there's a pause in class, just run. That's fine. Okay. If concentration of A increases, reaction shifts to which side? Products. So we're increasing this. So it shifts that way. Once again, I go back to my teeter-totter analogy. If that side goes up, it's going to slide down this way. What did I mean by those 3 words? What word would you put there?
Use
Sure. Use up A. I don't know what the original 3 words are. I know what it's supposed to be. It's going to be something about going down. If you increase A, Le Chatelier's principle, a shift will occur to blah, 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 blah. But the mnemonic, whatever you do, nature tries to undo. So if you increase A, the next thing that's going to happen is that A is going to go down. What will happen to the concentration of B? Decrease. So if it's shifting this way, this is going to get used up. So this will also decrease. We just say A will decrease. And what will happen to AB? Increase.
Why would A decrease?
Oh, we added A. What's immediately going to happen after we add it? It's going to increase it's going to increase this reaction rate, which is going to use it up, and now it's going to start going down. When we add A, which rate increases? Forward or reverse?
Wait, what? Forward.
Forward. If we increase the concentration on this side, the forward rate increases. Nothing happened to this side, so the reverse rate doesn't change. So the forward rate just increases. The reverse rate stays the same. Now that the forward rate is increasing, we're getting more AB2, so the reverse rate starts to increase to match it. I believe I have a series of, yes. Label those down below, and
You go back up one second.
yep,
Wait, Mr. Duval.
yeah.
So, you're saying after you add the A, it's gonna decrease.
Yeah.
Wait, but why don't you just say, like, put the arrow down because the rate is decreasing, but just call it 2A.
Which rate is
Or A.
which rate is decreasing?
Well, not the rate, but like the concentration of A.
The concentration of A is decreasing.
Because you're adding more A, so wouldn't you call it 2A instead of
Wouldn't I call it what?
2A? Like you have 2B.
No, that's just a balanced equation. A plus 2B goes to AB2. But I don't think I understood your question.
Okay.
You have to ask it again in different words.
No, it's fine.
Are you
I'm
sure?
positive I got it. No worries.
To look at A, let's do them in different colors this time. If I go to here, and this is where the change occurred, what happens to A? What would it look like on a graph? We just add some.
Up, down.
Spikes up. So boom. Nothing else spikes. In fact, I probably did that way too much. I got a little carried away. Now, if I increase the concentration, what does the forward rate do in response to that concentration? Speeds up. So what will happen to the amount of A?
Decrease.
It will decrease. Will it go back to where it originally was?
No.
No. We're above or below? Above.
Oh, what?
Well,
Like, why wouldn't it be below before then?
Did you see a problem?
why would it go below?
Like, are you, so the reaction like hasn't happened yet and you're just like, oh, I'm gonna add some more
Yeah.
A before I do the reaction.
Yep.
Yeah?
Yep. Well, the reaction was happening. It was at equilibrium. I added some A. It spiked. Now it's going to drop. You've added more. It's going to come to a new equilibrium. So this might be better if I talked about rates. And we've got forward and reverse. So my forward rate, let's make this T1. My forward rate is there. We added A. What's going to happen to the forward rate? It's going to spike. So it's going to start shoving things to the other side. Once it starts shoving things to the other side, what's going to happen to the forward rate?
So decrease.
Pardon?
Decrease?
It's going to decrease. Because as it's shoving things to the other side, it's decreasing its own concentrations. So both A and B are starting to drop. And so it will start to do, and it'll do that curve now that we're getting used to, where it drops and drops. And the reverse rate, as soon as it starts throwing things to the other side, what's going to happen to the reverse rate? It goes up. And it's going to be throwing a lot of stuff very quickly, so it's going to go up fast. And then as this drops, the amount of stuff getting thrown over drops, and so it also has the same kind of curve and it will overlap. And now we have equilibrium where it's the same, we have equilibrium. But the new equilibrium, both rates are faster. Because you added stuff. It doesn't come all the way over here, because although it's spiked, as soon as it starts to throw stuff to the other side, and it starts to go down, so this starts to go down, what happens to the amount of AB?
Goes up.
It goes up, and you get this, so AB starts to go up until it levels off, and it's throwing things back. So it'll never go back to the original one, because you've added more stuff to the system. A had a lot, spiked up, started throwing to the other side, goes down, but the other side is also working at a faster rate, so it will level out slightly above where it was before. So your new equilibrium would look something like that. Very apparently badly drawn. Let's see if I can't fix it.
Yeah.
Pardon?
You said it went below.
No, I said it did. I said it didn't go below. Someone else said it went below, and I said no, and then I tried to explain it with that. Are you saying that you heard me say it went below?
Yeah.
So what does B do?
I need to work on my enunciation skills.
Mr. Dufel,
Yeah.
what does B do?
So what does B do? B just flew along, and I didn't do these in different colors, but I'm going to choose to do that with B. And I won't worry about the ratio just yet, just in terms of what would it do right now. We're there, a bunch of A is added, the forward rate is increased, what's the amount of B going to do?
It's gonna go up and then decrease.
Why would B go up?
Isn't it the same as A?
We added A.
A is decreased.
If A increases, so we added A, we like dropped it in.
What, does it like stay the same?
Pardon?
It like stay.
Well, if we add A and this rate increases,
Yeah.
what happens to the amount of B?
Well, B stays.
Like this rate right away at the beginning is like going very fast, and this rate's like going really slow because we added a lot of A. So what's going to happen to that B?
Decreases.
It's going to decrease. Yeah, because it's making more AB. If this is going up, then the amount of B has to be going down. And so it gets that curve where it goes down and levels off. By how much compared to A will B go down? 2. It will go down twice as much because we use up 2 of them. So B goes below the line. And whatever, I think I over-exaggerated that. I'm going to fix my diagrams. This will probably irritate you if you've already drawn them. Spike, down like that, that looks better. And then that, was that roughly double? Yeah, it's roughly double. And this is
A
rate over time. And if this is X, then this amount is 2X.
Why did you add A? Why did you make it like higher?
This example is if we change the concentration of an equilibrium. So I just added A. So if A increases.
No, what was wrong with the graph before? Where it was like touching the line, you just made it like higher.
Oh, I realized my 2-to-1 ratio didn't look right. So I wanted this to look like half of that. So I just redrew it to be neat. Did that mess you up?
Yeah.
Sorry.
Is the change in the concentration of AB the same as the change of the concentration of A?
Yes, because it's in a 1-to-1 ratio. So that one should be how much? 1x. Because they're a 1-to-1 ratio.
Doesn't it say the green writing on the
Here,
graph? Yeah.
that says rate. Let's see what this thinks it says. It says, I'm not even going to try, it says if. Serves me right for trying to draw sideways.
Do you think it'd be fine if I got my water bottle?
Sorry, what?
Can I get my water bottle?
1 second. There. Before you go, has everybody got this down?
Yeah.
Any more questions? We're going to practice again? Again. Same reaction, we increase B. Andrew? What will the curve? Let's grab the old reaction. It was A plus 2B. A plus 2B goes to A, B2 plus heat. Andrew, what will the curve for B look like?
It goes up and then down.
How does it go up and down? Just like,
No, like, so it's gonna be like going up and then it's gonna slowly it's kinda like what we did the last page.
kind of like what we did in London. So it spikes up.
Yeah, it spikes up and then it's like going down, not like on a curve,
Like a curve like
kind of
like this.
not like on the other side. It's like a skateboard, like.
I like that. I like that. Excellent. Okay, run, get your water bottle. Everybody else, finish that off. What do they all look like? Is there a rate one below this? Oh, answer the questions.
You just look at the equation. So,
Your curves.
equation is A plus 2.
You're doing this, and then you're going like that, right?
Plus heat.
And the rate is fastest at the beginning, the rate change.
Increases.
So the curves are actually that. It's like a cliff.
Cause an increase
Because it's
in
faster.
the rate
What it means graphically when you do this
But it
is this implies it starts slow, gets faster, and then slows down.
And if it's increasing this
Right? That's a slow, fast, slow, where it's fast and then slow. You only want that part of it. Down.
the one that gets
Does that make sense, Nick?
yeah.
It's a very common thing because they look really similar, so the students often do them. I think it's very similar to
So
some.
it's just a sharp B.
It's just a sharp one at the beginning. Yeah.
I couldn't.
So, and it can have a curve to it, like you can make it like,
As well as the
because it doesn't have to be a straight line. You can go like,
Could be wrong.
whoops,
So A just
Yeah.
decreases.
you can make it like,
and then A down.
but as long as it's the fastest is at the beginning, so the steepest slope should be right there.
And then A B
Yeah. Then the last one,
Does this look right?
looks lovely. Are the ratios right?
I don't know.
X and 2x? Yeah. Good. Then just check the ratios and you're writing them in.
By yeah, you mean like actually yeah this time?
Yeah.
Okay.
Yeah. Honestly, sometimes I look and I just see like, you've done work and it looks vaguely good and I just go with it. Because we're gonna correct it in a moment, but it looks good.
The two X is the difference.
Put the little X's in to show that you know that what the ratio should be.
This will change like 2 times.
Oh, I see that was one.
I guess this is times one, but like how do you do?
Oh, that one doesn't have to be 10. Which one has to be twice what other one? That one. So the amount it drops should be twice whatever that drops.
So it drops.
I
This
have
drop
no
is
idea.
times two.
Yeah. And this increase is times 1. Oh, you're using this as the endpoint for 2.
So you're not supposed to do that.
No, I use that to show where the original line was so that you can compare.
Oh.
But I'm always interested in how people interpret that. 2x? Yep.
Yeah, but
How much did their ratio change? Oh, you got it there, 2x and x. Okay,
Oh my goodness.
I've seen most. A comes across. Compared to B, how much should it go down? Twice as much?
Yeah.
once
Compared to B?
No, once as much.
One.
B goes down twice.
half as much.
B should be twice of A, so this should be half the amount. So if this is 1x, this is 1/2 x.
No, we both agree about that.
So I can use fractions.
Well, you didn't
Or you could call it
Yeah.
1 and 2x. I mean, I don't know.
Yeah.
It's the same thing. And
Yeah, maybe we can do 11.
let's use another one.
Wait.
Because you just have to figure
What happens to AB?
I have
Question to you?
Shouldn't
the 1x be from the top point to the line?
Oh! I thought I drew it that way, but then I labeled it.
Yeah.
That should be, yeah. And maybe I put in a dotted line. Because it's this distance is 1x, and then that is half of that. Yep. The amount that it drops, because they're reacting. So A reacts with 2 B's. So for every 1 A that reacts, you should get 2 B's that are reacting. Who said what?
Wait, can you explain this all again?
Yeah.
Sure.
Same for the other one then too, right?
Same for the other one as well. When you add B, you've added to the equilibrium. This is the point right there at the beginning, and right there in which the change is going to happen.
Yeah.
And the change that's going to happen is the forward rate's going to increase because you increase B, and it's going to change as A plus 2B. That's the stoichiometric ratio, that's the balance equation. So you're going to use up twice as much B.
Oh, okay.
So B, starting from this point, the amount of B that you lose should be twice the amount of A that you lose.
Oh.
Does that make sense?
Yeah.
Yeah. And I totally labeled it wrong. When I put it down there, Tio caught that, which was good. I did it on purpose as an exercise for students to catch. It's an actual teaching technique. I think it even has a fancy name. What will happen to AB?
And then level off.
Increasing level off, and the sharpest change happens at the beginning or the end? Beginning. So you always start with that cliff-like, that, and that should also be 1x. I may not have drawn that well, but am I recording? I am. Okay. Now I think there's some questions down below. If you increase, and this is essentially just saying the reactants, if you increase the concentrations of A or B, what happens to the reaction rate? It increases. And then what? Decreases. And this, I'm going to star this, because some of you are going to get very, very upset with the answers to some questions. It doesn't just increase, like slowly. How does it increase? Quickly, it spikes. So if I said a question, if I add A, what happens to the reaction rate as it approaches equilibrium? What would your answer be? If I add A, what happens to the reaction rate as it approaches equilibrium?
It slows down.
Slows down. But if I said I add A, what immediately happens to the reaction rate? It goes up. And we asked both questions. So being aware of time, when is this occurring? Right away? Or as it approaches equilibrium, it's going down because it spiked to begin with. Whereas the reverse reaction rate is easy. What happens to the reverse reaction rate? Time, rate, forward, reverse, this went along, forward rate spiked, and then it came down. Reverse, went along, at equilibrium they're the same, then what does the rate do? goes up. It's gotta meet it, because that is throwing things to that side. It's like it's like if we were playing the game and we had the big wall of chemistry, and I just throw a bunch of ammo on one side. They're immediately gonna grab it and start throwing it around. Now they have more ammo. And then they keep throwing it back and forth.
So increase and decrease.
So the reverse reaction just increases. So the side in which there's the stress, it will spike and then decrease. And the side in which there's no stress, but now it's just reacting, since it's getting thrown a lot more stuff, it's just going to increase. Let's see what the next thing says. The next page is just that rate graph.
Wait, can I see that one?
Yeah. Good, Andrew? Okay, so the next page was, I was going to just tell you to draw that graph, and we just did it. So I leave it there as an exercise that you can do in the future when you're reviewing it. We're going to immediately go to this one, volume changes of the gaseous system.
Wait, so we're not doing this page?
We already did it.
Can I see it?
It was that rate graph. Right? If we have the forward rate and we added a reactant, it spiked and it went down. We just answered the question. Reverse rate, what has happened? It slowly comes to, and the next page I said diagram, and I already diagrammed it for you. So I'm just putting that there so when we go back to review it, we know what we were doing.
Does that say BC time?
BC time? What?
What's on the X?
That just says time.
Oh.
Clearly. Clearly that just says time.
What's the one before?
Grouping, ungroup,
That's one way.
grouping, ungroup, it's a lot of work. And it says apparently Tino, which means time in another language, Neufaldian. A reminder, if you go into chemistry and you develop a new molecule or discover a new atom, it is required by law and long-standing tradition that you name it after your high school chemistry club. I am waiting for a Neufaldian to appear. Volume changes of gaseous systems. So we've done it with concentration, we've done it with temperature, we haven't done it with gases. We've got that. What happens to the pressure if we decrease the volume? Does it go down or up?
Increase.
Well, everybody seems quick with that. Here, I'll demo it. Don't say other steps.
There's no.
So I don't know how C4 is actually where is that?
What are we on? Halo 3? Oh, the reaction rate.
How fast is this being produced?
So,
First, this increases because this increases.
we're still in phase.
So this increases, but then
No, we already were.
as this less increases, then the rate decreases. And then in the first reaction,
That's what I heard. I had a shower like that.
because this is just volume.
Shower that was like
distracted me there looking at the delegate.
Stay focused, stay focused.
Hmm?
Well,
I don't understand how it's just increases.
Hmm?
I don't understand how it's just increases.
Oh, back to the rate graph.
Yeah.
Yep.
Just like balance it out, this is high, so we have like balance out, this one, we usually stop. So like, he says this increases rapidly, because like you add it,
Thanks.
but in the overall after it actually decreases, because this
Oh,
one increases.
do you know what's fish tacos for lunch?
I don't know if that's good or bad.
No, I feel like it'll be good.
If you're fishing,
Yeah,
not
it's like
fishing.
guacamole.
The reason why it increases because it's adding, this question says that it's adding this shit, right? So when it adds that, this spikes.
Yeah.
Okay?
That's a really
This is the
big
forward.
balloon.
Really big balloon.
That is quite
Lots of potential.
And then
Lots of potential.
kind of like this.
Oh no, please don't.
And the
Like
reverse
cat.
reaction rate has to like catch up to that.
Yeah.
And it catches up by only increasing until it reaches like until they reach the same point.
I'll do it up there. If we have that reaction, A plus, let's just make it easy. I'm gonna take out the 2's and everything in it. If I increase that, what happens to, I'll make that one the different color as well. If we increase that, what happens to the forward rate?
Increases.
No. Pardon? What happens to rate if you increase the concentration? Louder?
Increase the concentration. Wait, what's the question? Say that again.
If you increase the concentration, what happens to rate?
Increases.
It goes
Everything
faster.
happens quicker.
Everything happens quicker. So we only increase the concentration on this side. So this side hasn't changed. So if I massively increase that, just spiked it, then the forward rate will go up. Does that make sense? So we've got a certain amount of A and B and AB. If that rate's going faster, what's happening to A and B?
Did it decrease?
No. Ask the question.
Yeah. It's gonna go down.
It's going to go down. What's going to happen to the amount of AB?
It's gonna slow down.
Is it, if these are going down because they're making more of that,
Oh, that's gonna go up.
that's going to go up. So what we have right now is this spiked, but now it's going down.
Yeah.
That is going down, and this is going up. If this rate is increasing, what's happening to the reverse rate? If the concentration of AB is going up,
Just going up.
it's going up. Because that concentration is increasing, then the reverse rate is also increasing. But because A and B are now going down, what's happening to the forward rate?
It's going down.
It's going down. And that's why you get that very distinctive curve where it goes like this. And so this one's going up, even though you had something on the other side, simply because it started shoving more stuff at it. So the amount of AB just went up. And so the reverse rate has to increase. Does that help?
Yeah.
Okay. And
So we would go.
if you decrease the volume, what happens to the pressure?
So if this was initially going
Yeah, decreases.
I'm going to decrease the volume.
No, you can't do. You can't.
I can't?
You can't decrease the volume.
I can't decrease the volume? Pretty sure I can.
Oh no. Then
And I think all of you know instinctively what happens if you decrease the volume. Because what's happening to the pressure inside as I decrease the volume?
It's compressing.
Yeah, it's compressing. And what happens to the pressure inside?
Oh, it
Increasing. And right now it's at an equilibrium.
So decrease in the volume equals
Increase in pressure, yeah.
Jesus Christ. That was so aggressive about Jill.
Yeah. One of the reasons I'm not allowed to do that Kemba Loving thing where we blow up the hydrogen oxygen balloons is because I literally induced a couple of panic attacks in some of the older teachers upstairs. And once a long time ago, I wasn't told to stop after that one, but a long time ago, a BFA showed up and was like, I'm here for first aid. Like they were ready to go. They had their kit. They thought like with that explosion, people were injured. And when I told them they weren't, I'm like, it's okay. They actually started going into shock because they were ready to treat injured people. So that's why we have to go do it in the other gym now. We scare people too much. But occasional gunshots are
Why
fun.
don't you clean the whole ceiling?
Pardon?
You had like a
I did clean the whole ceiling, yeah. It was so much mess. Okay,
People just be jumping to conclusions. Hello, that's wild. I'm gonna go first base, balloon ball. Like, that's crazy.
I think the most heartwarming moment for me was once when I did a demo with a Chem 11 class, and I was showing them different types of compounds, and I called a volunteer up, I held a cloth to their face, and then they fell unconscious. And I said, that was ether, like you know from the movies, it makes people unconscious. I had set this up with a student beforehand. There was nothing on the cloth, because that'd be way too dangerous. But another student in the class saw me do that, ran to the principal's office. Like, this teacher's dangerous, and that teacher is trying to kill someone. You gotta get them, I had to stop, like, they're okay, it's fine. And I learned my lesson after that. Don't quite seem like you're trying to kill students in class. Anyway, if we decrease the volume, oh, I forgot to mention the balloon. How many gases were in that balloon? Nuts, like name some of them. What were they? Oxygen?
Carbon dioxide.
Carbon dioxide?
nitrogen.
Nitrogen. For which ones was their concentration increasing?
All
All of them. When you have a system, if you decrease the volume, it increases the pressure for all of them. So if you decrease the volume, you increase the pressure, and you increase the concentration of all gases present. Now I can't do it very well with a balloon because I have to find a way to attach it like this. But if I did manage to have a box and I pulled the gases apart, I increased the volume, what would that do to the pressure? Decrease. You're creating a partial vacuum. And what would that do to the concentration of all gases? Decrease. Andrew, question?
No, I'm like figuring it
Okay. I think below that we have a question. Oh,
Even with your own writing, it's still
that's such a nasty example. I give you that as your first example?
Oh, yeah.
I just don't feel like
Maybe don't.
Yeah, that's silly. Skip the first example, that shouldn't be first. Go to this one. Go to this one, go to this page. We're skipping the first example, I'm gonna come back to it.
what? Why?
Because that's
Yeah.
this first one seems easier, it's not.
If everything's just
Using everything we just said, if you increase or decrease the volume, it affects the concentration of all gases. And then thinking about the phrase, whatever you do, nature tries to undo. So this is a system in a balloon. It's in some sort of container, and we're going to decrease the volume. Which way will it shift? And which will it shift towards reactants and products?
Reactants.
Why?
Well, because there's more like instability or like gases on the reactions.
There's more gases on the there's less gases. How many gases are here? Two. And how many gases are here? Three. That is important. If I decrease the volume, what have I done to the pressure?
Oh, you've increased it.
I've increased it. How could this system undo that?
release.
How could we decrease the pressure just by moving the equilibrium around?
Two products.
Two products? Why?
Because then less.
There's less. If this reaction shifts this way, this takes away molecules. And if it takes away molecules, then the pressure will start to go down, and that concentration will start to go down, so it'll shift that way. And that way you'll get more NOCl, but you get less NO and Cl2. If you have, like here, that particular reaction, hold it. It says old flash animation.
Bro, I did something today.
Now I don't want to look in the Microsoft store.
I've been on shift for almost 13 hours today.
Nah, let's get it out of here. I'll do that later. Clearly there's something I'm not on my machine that runs it. If I've got, let's say that this is 1 liter.
Third block. After third block.
Are we going back?
Gentlemen, chemistry. I'm just going this to demo it. This page is for me. You can't write any notes on it. So we've got this type of reaction, was similar before. I've got 3 stars, and it's in equilibrium with a bunch of happy faces. So let's say this is the equilibrium. If this is 1 liter,
We need one.
what is the total concentration of everything? Like in terms of pressure, how many particles are in there?
16.
16. So we got 16 particles per liter. And I'm using this concentration as a stand-in for pressure. It's got a certain pressure. Maybe it's like a balloon where it's keeping the sides open, or maybe it's just like a steel box, and that's how much we've got in this. And then I take this,
That's 14.
There's 14.
What if that's 14?
1, 2, 3, 4, 5, 6,
now
7,
14.
8, 9, 10, 11, 12, 13,
So if you're
14.
missing a happy face, because it's not.
What?
You're
Sorry?
missing a happy face.
Why am I
You have
missing a
5
happy
happy
face?
faces and 9 stars.
Yeah, so?
You should have 6 happy faces. 'Cause
Why?
3 are 3.
But does the concentration depend on the stoichiometric ratio?
Doesn't it?
No?
Yeah.
No?
Oh.
If you have a reaction, I mean, this is not an equilibrium reaction.
Then what's the stoichiometric ratio for?
Let's go back to here,
Yes.
where we did it. Did these concentrations correspond to their stoichiometric ratio where you started from?
No, but
No.
what's the
But the change will. Right? So they could start off at anywhere. If you don't like that ratio, we could start off, which one do you want more of? Because I can do this demo with any particular amount. See how it works. We've got 14 particles per liter.
Just because of concentration.
I'm going to make it smaller.
Lose 2 to 3.
And now we have all of the particles are stuck in a tiny little box.
Or they just like more.
So now they're more, let's just say instead of being 1, this is now a half liter. What's our concentration?
28.
Now we have 28 particles per liter, right? Immediately this can now fix that. How can that fix that? Which way did someone just said it was going to shift in a particular way. How can we reduce the number of particles in there?
Put them into stars.
Yeah, which way does the reaction have to go? Products. So we take out 3 stars. We have to add 2 happy faces. But now we've changed. I'm going to just line it up nice and neat. Obviously, a real gas wouldn't like that. And we could take out another 3 stars, if it's not there yet.
2.
And then add in another 2 happy faces.
Oh.
Now what's our ratio? How many particles are in there?
Right.
1 to 3.
How much?
1 to 3.
No. Total number of particles.
Oh.
12. So now instead of, we've got 12 per 0.5. So we've gone from 28 to 24 particles per liter. It's dropping. Now, the new equilibrium might still be at a higher pressure than it was before. But now that we've taken some out, what's going to happen to this rate here with the happy faces?
It's going to decrease.
We've got, which side do we have the higher concentration on?
Products.
We've got lots now of products. We've made some products to try and adjust to that. It's going to start throwing back, and eventually you'll get a new rate. This might be the new equilibrium. Far less than it was before. We've got fewer stars, but it also decreased the pressure a bit. Whatever you do, nature tries to undo. I can't do it with like numbers yet because we haven't introduced that. I believe that's the next PLO is where we actually put numbers to this, and you can calculate where it would be. But you can see what it could reduce the pressure just by shifting the equilibrium. But when you shift the equilibrium, you're going to have a return rate because now you're increasing the concentration of that size. So as soon as that happened, it went there. Another way to think about it is if this side has 3 things and this side has 2 things, which side is most affected by concentration? For which side does it matter more? Which one has the most stuff? Reactant. So this side is going to be affected by concentration far more. It's got more stuff. This side has less stuff. It's not as affected by concentration. I mean, decrease the side of the box. These things are going to react to that more. It's a bit like the heat term. When you added energy, the side with the heat that was most disadvantaged had the most benefit. When we increase the concentration, the one that's most at a disadvantage from concentration, because it has the most different kinds of stuff, gets the most advantage. Same with if you increase the size of the box. If I made this box huge, then which way could it shift? To make more.
To the right.
To the right. We could then make it, oh, come over here. These are the ones we took out. So if I take these out, and we had it at a liter before, but now we make it much, much, much larger. Maybe now this is like 2 liters. What can it do to fill up the space? What will I take out? Smiley face. And what will I add in? Stars. So I'll take out 2 smiley faces, and I'll add in 3 stars. And now we've increased the total particles. I can take out another 2 more, add another 3 more, and just keep doing that process. And now as we're doing that, which side has the advantage in terms of concentration now? Stars or smiley face? Stars. So eventually that rate is also, as I start doing the exchange to adjust for the pressure, the stars concentration's going up, its rate is going to increase to compensate, and then you're going to get a new equilibrium.
So when we're talking about reactions, like shifting,
Yeah.
would it shift to the one with the higher pressure or the lower pressure?
So if you lower the pressure, it'll shift to the side with the high, that will give it higher pressure.
Okay.
If you increase the pressure, it goes switch to the side that'll give it lower pressure.
So if reactants are like increased, then it would shift to the reactant side.
If reactants, no, that's, you're asking about concentration. I'm just moving volume, I'm not adding anything. I'm just changing volume.
Yeah, no, so I'm saying like if you increase the reactants, it would shift to the product.
Yes, but that's concentration.
Okay.
Because if, this is a really good point, because students are, if, for this reaction, if I change the volume, am I changing it for the reactants or the products? Both. You can't change the volume of only one side. A reaction is us describing in words what's happening in nature, but the actual reaction is on both sides at the same time, like the whole thing's in the balloon. So I can't, for a gas, I cannot change the volume of just the reactants. There is no bulb of just reactants. It's reactants and products. I've gotten a couple of questions about, what was it? ClO2 goes to Cl something, Cl2 plus O2. I don't think that was it, but let's say that was it. And these are all gases. And this is from your Hebden, older question, but if you made this pure, like you went in the lab and you just made pure ClO2, chlorine dioxide, why will it not be pure? You made it pure, and it's just, and you just put it in a balloon, and now it's not pure. Why? Yes? Pardon? Which particles? Yeah, so you made this, that's all you have just that, you put it in a balloon. What's the equilibrium going to do? shift to products. Because you have it. So it's going to have a high reaction rate, it's going to come here, and then it will immediately be diluted by its own product. Anything that's in equilibrium, you cannot make pure. Because as soon as you put it in something, it's going to make its products. If I made these and I put them in a balloon, I had pure chlorine gas and pure oxygen gas, and I put them in the balloon, is that going to be pure? It'll immediately have a reverse reaction and make that. We'd probably write it the other way around if I just had those, because those would be the reactants. So gases are always in just one big balloon. You can't separate the two sides. That was a lot. Try and graph it. What? Okay.
That's the sign when your brain
It's like 12:50.
Yeah,
You can't get rid of this. It's chemistry 12. We need every second. But I will say that the last few minutes have had a lot of brain things in them. Why don't I say the last 20 minutes? 15, 18 minutes. Get out your head there.
Yeah.
Do some work, your own work.
Did we go lunch?
No,
Early?
no, it was just asked. You weren't paying attention.
Okay, you did.
Yeah. It was a good try. Yes.
Well, if it's not we, what if it's just I?
So shift over, so
Bro,
that should go up.
that was a double fault.
I didn't know you were gonna.
How?
So what I can't tell are those
Don't make it 2x from that, bro.
What? That's
Okay, so the first thing that's going to happen, if I decrease the volume,
Oh, I got that.
what happens to the concentration of all
So
of
I'm
them?
guessing you also have an idea.
Oh,
They all spike up, and then the reactions happen. That's the only thing.
Oh, that might be like 80%.
If you want to show me what happens to this one as I come around, whoops.
That's the thing about the quiz.
Well, hold it. I'm on that page.
It, like,
Where am
drops
I?
your index by so much. So if
Where
you
is it
get
supposed to
one of
be?
the 6 wrong, you're already like 75.
Yeah. You want to show me what happens on that one? I'll tell you if you're on the right track, or you can get out your head.
It's either get 100 or 80%. So how are we doing PLP?
So you're looking at whether the volume is increasing or decreasing. That tells you the pressure thing. Yeah. So you have to do the volume. So you increase the volume. What happens to the pressure?
Yeah, I don't understand how we're supposed to do this.
Think of what I did with the balloon. What did I have to do? I had to make it smaller to make the pressure go up.
What if it
So,
was
and this is like never had a pressure just like that. You're making it vacuum. So you increase the volume, you decrease the pressure. If you decrease the pressure, which way is it going to shift?
That's zebra.
That's what I'm kind of confused about, because don't all these.
Yeah.
Like how many?
There's also a trick with that one a little bit.
Wait, I can't hear. I don't.
The trick is that the equation's not balanced.
How is something little?
Once it's balanced.
Oh, and okay.
Why would
That's way gone.
Poor gal.
So prefer to snipe it.
But what equations no one?
That's too many. Why do you have a 4 and 2? You have a 6 then? Oh, okay. Yeah, 2, 3, yeah. Okay, sure. So which side has, so you increase the volume, decrease the pressure. Which way could it shift to give it more pressure? It's the one with, yeah, because the molar volume of the gas particles all act the same. So it doesn't matter what species it is, the pressure is affected by all of them. So to increase the pressure, it just has to shift that way, and it turns 2 particles into 5 particles.
So this one is a shift.
But, now what?
Yeah, it's okay. I like how cold.
If you increase the volume,
Bro, I have the best.
what do you do? No, you increase the volume,
So
you
it's-
have to decrease pressure.
That class is so, you switch?
Right.
You should, you can still switch probably.
It doesn't matter.
And for gases, pressure is another word for
And she lets you read it
concentration.
while you're-
Concentration also goes down.
So as long as it's not like a cross.
So the first thing that happens, is you increase the volume, what happens to the concentration
It
of
doesn't
all
let it
gases?
go through.
I don't know, Scarlet makes
every
you do a lot of
single
acids, so if you're
paragraph.
bitter acids.
They all decrease.
Like, I'm not.
And then the adjustment curves
I don't
happen.
know.
So they all
I'm
spike
trying to
through
fix
that.
it.
Bro, I must have done this, all I hear is okay, yeah.
That makes
Liquid?
That's
love
all I hear.
liquids.
Actually, I don't know, cause every time I talk to someone, they're always like, oh, his headphones gave me like a developing.
Paragraph starts.
Because it, like,
Bro, Josh.
I
Pressure
heard
is
like,
affected
like
by
someone is not
Rate has it.
The more
Oh yeah,
particles
she
you have.
grades
See,
you
you
the more pressure.
depending on what you want to
Yeah, you
do.
come to
Here's what I'm trying to
So if you want to do engineering, she's gonna give you like, or she,
I'm very
Um,
invested. Integration is great.
Yeah, Joy, hold on.
she grades you depending on where you want to go. I
If-
don't know.
Oh.
I just push into, if I'm.
Like she's like, oh yeah, you have to do a lot of writing and like say
Oh.
this, so I'm gonna grade you.
So the
And
reaction.
she knows
will
doctors
move
have bad
through
writing, so she's like, oh, I go to medicine. Easy.
So it's taking up two, because now it doesn't have any pressure. Because it doesn't have any pressure, it's gonna shift that way.
Bro, I got the though.
I'm a great.
And add.
It was good. But I got an exciting and then I went and
Now,
ran for it.
in terms of why it does that.
From
when
setting
you
to
say-
setting
when you
eyes is a
say
big difference, it's like
decrease the
90,
volume,
67%.
these things actually hit each other and affect orientation.
I shouldn't
and
guys
everything.
even know how to do it.
And that is,
Extending highs only
that's
there.
gonna happen more often.
Yeah. It's not
Whereas
enough.
this, it doesn't have to do as much. And so it doesn't matter as much to it if things are more concentrated. So the change of pressure just affects the side from which more particles can emerge. You decrease the concentration, decrease the volume and decrease the concentration. Then that really affects the side, and so that way its rate slows the most, and you get more of it.
But this, it's always shifting to this.
It's always shifting towards or away from that side. So if you decrease the volume, increase the concentration, that matters most to this side, and its reaction rate goes faster that way, faster than this one does. But the mnemonic or the quick way is if you decrease the number of molecules per square centimeter, it will shift the side to increase the number. If you increase the number of molecules per square centimeter, so you jump it down, that will shift the side to decrease the number, say 5 meters. Yeah.
Is this right?
Yeah, they all go down, do we come up and down?
And this one goes down.
Yep, down.
2 hours after.
And these three,
And we get
goes down, yes.
an hour
Yep.
before.
I heard that you were.
Wait, do you want, are you doing that or transfer?
Oh, okay.
Yeah.
You got two points.
Are you, oh, did you already?
Where are you applying?
Yeah. Oh,
I'm going to Australia for
My mom.
oh, so,
You're going to Australia?
are you going?
for direct entry.
Oh,
Oh, it's so nice. Like,
Wait, did you already get this?
no, I can't do applications until.
Oh.
And then they only send
I
out
was a little worried.
offers
You
for
can say
something.
Or you can say
That's
it's
Australia.
I know because it's below their place, so there's schools backwards, so their summers are.
Okay.
Yeah, you give them the vibe. You give them the vibe. Like, light that up, so yeah.
It's a speed walk.
In the best way.
Oh yeah.
Do you want
I'm
to?
the guy everyone's
Wait, what's
scared
your
of.
last name?
You look a little bit,
Yeah.
and I think sometimes you make little mistakes because
I know.
Like the test
What else should I
was
write?
good, but it
Like
could have been
experiences in the, like,
Yeah.
something.
No, not polymers. Just the mom.
You get like pediatrics.
Oh, yeah, it's more.
Do you want to go to
I
Silver?
just-
Yeah.
Don't
I want to get to med too, but I'm really
No,
interested.
that's fine.
Yeah.
Okay, that's fine. I'll talk to your advisor, we'll make the change tomorrow.
My sister.
Where do you apply nursing?
I applied for.
Oh, I could
I was gonna
override
let them
Spice.
go, but you might as well do
Yeah.
that. Like in school.
This would be so good for
Yeah,
you.
that was something.
Okay.
Like Dalhousie, West.
You're doing weird things with it, don't do that.
It's really big for
Don't do,
I like a lot of like happy pounds per day.
don't do things like,
Yeah, we do.
nothing ever goes back up and goes down. There are spikes involved, so things may spike up or spike down, but then they'll curve in some kind of way,
Well, you're
right?
just
And sometimes they'll spike down and then go like that can happen too. But you'll never get it go down and then go back up again.
Yeah.
To start you off, what will happen to the concentration of all the species when you increase the volume? They all spike down. Yeah.
look at my husband.
Do I have to do something like this?
I like
Come on.
I had to do something?
You make some people about that, or that is really help.
Yeah, right.
Yeah, go for it.
Are you writing all the PLOs?
Well, I wrote like things that like
Sorry,
key
gave
info.
up? Yeah, okay.
about
Sure.
each one.
If can we please get early lunch?
No, we have great jobs. You need to work every spare second.
So
Every spare second.
Then you can find the limit of the equation from like the
No, that's not a break, that's just leaving. That means I'm a junior, you're not a junior.
and the positive side, and if they're equal to.
Now you're a senior, you're full time.
Well, I'm not working
But in the five percent.
Yeah, but I can only, lead a horse to water. You can't make it, so you're here. But if I say you can go, everybody will
Bro,
stop.
I went to bed at like 12.
Yeah.
Like 2 a.m. working on like his portfolio.
But what you could do, is a lot of fun stuff.
5 squared
You could go help other people.
25.
minus 14.
Yeah.
Who's your
I don't know. Let's go to
25
11.
minus 14.
11. Let's go to 11.
Okay, 11 equals 11, which means that the limit from the left side is the same as the limit to the right side.
Yeah, you said
So
it.
they're equal. You can square the same shit.
Yeah.
Okay. That's like a lot easier than I thought.
It's really.
How are you doing?
Good.
Okay. Do you have, is anybody in the same house as James Winkle?
Yeah.
Okay. He's left his Hebden book here for like 3 days, so if you tell him it's down the line.
Like sheets, your notes to us with our code names.
Oh, I haven't put it up yet.
You don't have to.
Let me double check, I think I got the last code name.
But it's okay. I'll just make it better.
And then, because I was waiting